header checksum. The reason why header checksum has been removed is because this header checksum was designed to provide an extra protection for the header, and that extra protection is not really needed. And considering we already have protection, error control at the link layer and also at the transport layer, so we might not need the error control in the network layer again. So it has been removed. And the only field that has been added in IPv6 will be the flow label, which is the identifier to uniquely identify a flow instead of a packet. For example, on the left-hand side, you see identification, which is used to identify the packet, not a flow. But here, flow label is to identify a flow. A flow, by its definition, is a stream of packets that have the same source destination IP address and source destination port numbers, which we will see in the next chapter. I mean the port number. So the flow label can be used to identify a sequence of packets that belong to the same flow. And we have mentioned these changes last week. And since we moved the options into the extension headers, including the fragmentation, so all these are shifted to the extension header. In IPv6, you could have many extension headers. That is right after the IPv6 header. Okay. And after this extension header, then you would have most likely the transport header, either TCP or UDP header, and then the data. It has defined a number of extension headers, and with their number, these numbers are used to identify the type of next header, or the type of these extension headers. And usually they are, in fact, they are actually the protocol number. If these are protocols, say IPv6 with the protocol number 41. And the standard says that you need to use this extension header in the exact order of this. That means you can say I use a routing header first, and then the next header will be a hop by hop option header. No, you can't do that. You need to put the hop by hop option header first, and then routing header. You can reverse these two. It depends on, well, it depends on the, well, if in processing these headers, if the program are implemented in the way that it processes this header in sequence, then it is needed that these headers are put in the exact sequence of this. Okay. However, these extension headers, they are not processed by the intermediate routers. They are only processed by the host, end host, except there's one exception, that is a hop by hop option header, which is also processed, which will be processed by the router. So what it wants to do is to simplify the processing at the routers, so that the router can be fast, and put the complexity to the end host. Okay, and each of these extension headers would occur at most once. So you can only have each of these appear once, but there's one exception, which is a destination option header, which could occur at most twice. Okay, this is the fragmentation header, which we have seen fragmentation in IPv4, and here it's in IPv6. It's basically the same idea. You have the identifier. If you need fragmentation, then you need an identifier to identify the packet. But if you don't use fragmentation, you don't need the identifier to identify the packet. So in IPv6 header, there's no identifier. But in case you do fragmentation, then you need an identifier in the extension header. I mean the fragment header. So you have identifier, and you also have offset, and you also have a more bit. So with the offset, more bits and identifier, you can do the same thing as IPv4, except that now it's in the extension header, not in the IPv6 header. Okay, here's an example with the packet fragmented into fragments, and each of these three fragments would have a v6 header followed by fragment header. And we also mentioned that in IPv6 fragmentation, it is only done at the end host, at the source host, So you do fragmentation at the source host, not at the router. At the router, it doesn't process the extension header mostly, and the reassembly is only done at the destination host, which is the same as IPv4. But in IPv4, you can do fragmentation at routers, but in IPv6, you can't. The fragmentation is only done at a source host. So for the source host to know the MTU of the entire path, for example, when we say MTU, we usually talk about the link MTU, not a path MTU. However, because the source host needs to do fragmentation if needed, and the routers cannot do fragmentation, so you need to find out the MTU along the path, so which is called path MTU. So there's a mechanism called path MTU discovery to discover the MTU the minimum MTU, the minimum link MTU along the path. Suppose there are 10 links along the path, and I need to find out which link has the smallest MTU, and I would take that smallest MTU as the path MTU. Okay. And here there's the port IPv6 it requires that every link MTU must be larger than 1280 bytes. So you can assume that a link MTU is always larger than this. But if you need if you like to explore the path MTU, which might be larger than 1280, then you initiate a path MTU discovery to probe the path. So you probe the path to find out the path MTU. If the value is larger than 1280, then you can use a larger MTU. Okay. The next issue to look at is the IPv6 addressing. Like IPv4, it has unicast and multicast, but it also has anycast, which means that the destination is one of a group of destinations. It could be any of them, any of the group, any one of the group members. Okay, and here's the way they represent IPv6 address, and in hex decimal, and since it's 128 bit in length, so each hex is 4 bit. So if you have 4 hex together, then it will be 16 bit, and you need 8 of such 16-bit hex. So then if you have 8 of such 16 hex, then you have an address of 128 bit. So each of these is 16 bit, and you have 8 of these, so that will be 128. So this could be very long compared to IPv4. It's almost impossible to memorize. So in fact, it's not meant to be memorized. Okay, and if you have as you can see that some of the hex here are all zeros, then you can put a representation of this into this, for example. So if you have consecutive zero, consecutive null, then you can abbreviate the representation as this. And within this huge address space, right now we only have a small percentage of address being allocated. For example, this, mostly here, the aggregatable global unicast address, which we just grab 1/8 of the entire address space to use, and the other part mostly are unassigned, and some are used for other purpose of addressing. For example, site link local and site local, and also multicast. So mostly we are using the 1/8 addressing space, which start from 001. And within this address space, within the address space, we would have structures inside, and there are two special purpose address. One is 00, which means unspecified, and the one with 1, 0 and then 1, that'll be loopback address. And we also have special purpose address, which are IPv4 compatible or IPv4 mapped IPv6 address, and that means they are lower order address, low order 32 bits are from IPv4 address. So they are actually a IPv4 address, but append with a prefix of this. And also some address for non-IP devices. So if you have non-IP devices, then you could give them IPv6 address. And most of the address, unicode address, will be would have a structure like this. This will be the normal case, where you have the prefix in 3 levels, which are top level, next level, and side level. Okay, that is the network address, but divided into 3 levels. And then the host number, which is called interface ID. And if we use the MAC address, as part of the host ID, or sometimes called interface ID, then because that MAC address is 48 bits, however, the interface ID is 64 bits, so you need to add 16 bits further in order to constitute a 64 bit. So that'll be you have 48 bit MAC address, and you add up. This is your 48 bit address, MAC address, and since you need to construct a 64 host ID, so you need to lengthen. The address from 48 bit to 64 bit, and the way you do that is as you can see, that you add this FFFE. Okay, you need to add 1 byte, 2 bytes in the middle, within the middle of this MAC address. So you add this, so now it becomes 64 bit, and this address will be here. Start from here, and then here. This should be a 0, 02, 02. So it'll be here, and then add up with the prefix. In this example, it's a link logo address. So add up with the header and plus the 64 bit interface ID. So in a sense, we can use MAC address as part of the IP address. And that also has a problem that a host can be traced from its IPv6 address. For example, if I use my notebook travel to a hotel, in IPv4, I get my IP address from the DHCP server, right? For DHCP, we will see it in the next section. We'll see that in DHCP. So we got an IP address. And that IP address, I will use that IP address to send a packet to anyone I need. Okay. And for those who get the IP address, get my packets, they would not be able to see, who I am. Because the IP address cannot reveal the identity. However, in IPv6, because my MAC address is a part of the IP address in this configuration, my MAC address is part of the IP address. So what happens is that if I send packet to someone, then that someone can use the IP address to identify, okay, this MAC address belongs to someone. So I know exactly who is sending the packet. So that will reveal your identity. So that will be some privacy leaked, with some privacy leakage. So in this example, in that configuration, the MAC address will be seen by others, and and this is not going to happen in IPv4, but it happened in v6. Okay, the address space has been allocated to many regions, and in Asia Pacific region, it's APNIC, and then under APNIC, it distributes allocate the address to the NIC of many countries. Okay, and here's the MAC address space that that also decompose the address, the prefix into more levels. So you would have no local, link local, site local, or global scope. So that would be those scope information here will be used to limit the scope of the multicast. Suppose I'm using the multicast group ID, but I also put the scope here to limit my multicast to very limited scale. For example, link local. So then the multicast, even though if out of this link local scope, there are also multicast members. But since I limit the scope to link local, so members who are outside this scope would not receive the packet multicast to this group ID. Okay. So in a sense that this scope attribute it will be used to limit the scope of the multicast to a smaller scale. Okay, and these are the prefix used to specify the scope. And well, they are the spatial address for either all nodes or all routers or all DHCP servers. Okay. So the next, the final discussion about IPv6 is about a transition from IPv4 to v6. And we are not going to upgrade all the routers or all the hosts simultaneously from v4 to v6. So they are going to coexist for quite a long time. In fact, for many years or even decades. So about the transition, there's some assumption that no flag day, meaning there's no overnight transition, and the transition will be incremental, possibly over several years, and the transition should be transparent to end users, so that end user would not be aware that we are transiting from v4 to v6, and it is assumed that v4 v6 coexistence will be quite a while. And the transition approach are three. There will be three approaches. One is called dual stack, meaning you will try to make more host and more router to be IPv4 and v6 capable, meaning that they can recognize, they can receive, and also transmit both IPv4 and v6 packets. So if they can do that, then the coexistence will be easier. So they can process either v4 or v6 packets. And the second approach is called tunnels. unfortunately, it's very difficult to make all the hosts or routers dual stack. So what you need to do is to either use tunneling or use translator. So these two approaches will be used to do the interconnection or internetworking. And for tunnels, it means that you suppose you have the source and destination are IPv4, but they need to traverse a network of IPv6. Then, or the other way around, you might have two end hosts which are IPv6, but going to traverse through an IPv4 network. Then what do you want to do? For example, in this configuration, the end hosts are v6. I need to traverse across v4 network. Then what you want to do is to encapsulate v6 packet within v4 packet, meaning that you would have IPv6 packet which has IPv6 header, and then you put another IPv4 header in the front, and that IPv4 header in the front will be used for tunneling. So in the sense that you would have a configuration like this. This is v6, and you need to traverse along a v4 network. Then your packet will be here. The packet will be this. This is IPv4 header, and this is IPv6 header. And in the sense that this for example here, so this will be the one with IPv4 address, one with IPv4 address. So I'm establishing a tunnel between these two. Let me take this out. Okay, so we are saying that we have in order to to enable these two IPv6 to talk to each other, we need to have a tunnel between these two v4 addresses. So we add up another IP header here. So the source, this will be the source. There will be a source address and destination address. This will be this. This will be this. How about this? There's also a source and destination here. The source will be this, and the destination will be this. So I have two headers. One of the headers saying the source and destination are these two. Another header in the front will have a source and destination address of this. So these are the v4, sorry, v6 in v4, v6 within v4, v6 within v4 tunnel. And for this, you need to manually configure the tunnels, or either manually configure or automatically configure tunnel. Okay. And the translator, if you don't want to do tunneling, then you need to translate the V4 packet. For example, in that case, then you need to translate the V6 header into V4 header. So if this is a IPv4 network and you have translator here, then the translator needs to map the V6 packet into V4 packet. That'll be called translation. So that is another possibility of internetworking these two together. However, in translating V4 between V4 and V6, because their headers are not exactly compatible. Right? They are not compatible exactly, as you can see. Some header fields are gone, and some new header fields are added. For example, the flow label. So if you do the translation, there'll be compatibility problem. For some of them, it's not a big deal. For example, if you want to translate a V4 address into V6 address, which is easy, as you can see, we have IPv4 mapped IPv6 address, or IPv4 compatible IPv6 address. So you can take IPv4 as a part of the IPv6 address. So for that kind of translation, it's easy. But for translation that would have the checksum, okay, from if it's from V4 to V6, then the checksum will be removed, which is easy. But if from V6 to V4, then you need to add the checksum, the extra checksum value. So those kind of compatibility issue, need to be handled when you do the translators. Right now, most transition, most of V6 coexistent, V6 and V4 coexistent model are by dual stack and then tunneling. But fewer rely on translators. So mostly rely on the first two approaches, dual stack and tunneling. Okay, we have an open source implementation of IPv6, and this is in IPv6. It uses the way they implement routing table is by a tree. So it's actually a tree structure. The table is organized through a tree, not a hash table anymore. Here, it's a tree, and the tree have left child and the right child. So you do the when you do the routing table lookup, you do matching here, and to decide whether you should traverse to the left children or the right children. So it's not by hash table anymore, but we still don't know how well this data structure is going to work. Well, you can do the experiment if there are a large number of routing table entries to see how well this work. But as we have more routing table entry in IPv6 routing tables, we will see how well this is going to work. And here, the tree is organized into this with the left-hand children and right-hand children. So that basically finished the discussion on IPv6. Next, we get into, so we have finished the data plane protocols, including IPv4 and IPv6. Next, we will look into the control plane protocols. control plane protocol, and we will look at 4 topics. The first one is address management. Address management, which include address resolution and address configuration. The address resolution is done by ARP, address resolution protocol, while the address configuration is done by DHCP. And then the second topic is on error reporting, which is done by ICMP. Okay. And then the next 2 are on unicast routing and multicast routing. For unicast routing, we look at they are divided into intra-domain routing and then inter-domain routing. That is within a domain or between domains. And the control plane, the data plane v4, IPv4 and IPv6, they are implemented in the kernel. In Linux, they are implemented in kernel. But for the control plane, the routing and multicasting, unicast routing and multicast routing, they are implemented in the daemon, process, so in the user space. But in the error reporting by ICMP, it's implemented in the kernel, almost together with the IP protocol. So this is in the kernel. How about the address resolution and address configuration? The address resolution is also in the kernel, ARP in the kernel, also in the network layer, like ICMP. So together with ICMP in the network layer and in the kernel. Okay, the address configuration is actually implemented as a daemon. So you will see DHCP-D, which is a daemon for DHCP. Okay. So in the kernel, in a daemon, in a kernel, and this in the daemon. So you will see a protocol, a daemon process called Zebra. It implements many routing protocols, and it's a daemon process. And same as multicast, mostly in the daemon process, but need to add something to the kernel. I mean, add the routing table, the data structure into the kernel. Routing too, they will do the computation in the daemon. They will do the computation in the daemon, but they need to write some data structure into the kernel. That's because the routing in the daemon in the user space, but the forwarding is in the kernel space.